Hi, Emily. Oh, wait, sorry. Okay. Risha, your answer was for the morning wake up question. Understood. I was like confused for a second, but okay, 25. Yeah, I feel like I might choose 25. Maybe a bit older. I'm not really sure. There's like a balance between being young and like mature. So awesome. Thanks, Kalia, for doing the do now. Hi, Clarissa. Also, Kalia, no worries. Thanks for letting me know. Thanks for letting me know, Jordan. Yeah, so the usual stuff, just have your cameras on. But again, there's people messaging me just for whatever reason. If you can't have your camera on today, that's totally fine. Just let me know. And then the list was updated. I think to there, you were added to the list for video optimizations. So just letting you know. But yeah, everyone should be working on the do now right now because I don't have too many responses. Hi, Kaylin. Hi, Danielle. Okay, no worries, Risha. Thanks for letting me know. Okay, a lot of people choosing 25. Yeah, interesting. Yeah, 25 seems like a good age. Emily, you said your brain will be fully developed, and yeah, I think that's the case. I think guys like brains develop later or something, but I don't know when that actually happens. So if anyone has any like psychology knowledge, feel free to share it in the chat. Savor, you said the age you'd want to be is 100 million. I think, didn't you on Thursday, you said you wanted to be a hitman if you could choose any career? That's you have some very interesting answers. I feel like at 100 million, you'd literally be like a rock. Yeah, anyway. Awesome, thanks to Vera for submitting your do now. I'm gonna give a couple more minutes on the do now just because I still don't have that many responses. Thank you, Brianna. Yeah, I would say the second question on the do now is a bit more challenging today. So if you're able to get it, that's really great. For the second question, if you're working on it, remember it's asking for the slope graph. So it's asking for a derivative, essentially. So the graph is the derivative. Hi, John. Hi, Marche. Hi, Kimura. So for everyone who just joined, people are working on the do now. Just have your sound muted, video on, and I'll give you a few minutes to do the do now, but not the full time. Cool. So I would say answer A is representing for the do now. Answer A is representing the original function, but we're asking for the slope of f of x. So like the slope graph. So it's kind of a difficult question, but okay, I'm gonna give 2 more minutes or so. Gotcha. Awesome. I'm seeing some right answers now. So okay, one more minute. Hi, Kimura. If you can, just get started on the do now. And I would like for everyone to have their cameras on. So if you currently have your camera off, please turn your camera on. If you can't do that, just message me. Okay, like 30 more seconds for the do now. Okay, thanks for letting me know, John and Emily. Also, yeah, so after you complete the do now, just make sure you get your notebooks out as well. Okay, so hi, Steve. Okay, so quickly, I'm going to address this fifth point on the intro slide. So I was looking at the submissions for the second homework packet, and I think I need to change something with how I do homework packets and stuff, because I would say a big portion of the class wasn't able to submit the homework packet by the deadline, which because it's such a big portion, I feel like, I don't know, it's like on my end, I have to change something about how I administer homework. So I'm gonna send out an update email today. So if you didn't submit it, like don't panic or anything like that. You're gonna have, don't worry about it. And I'm probably gonna change in the future how I do homework assignments. So look out for an email later today that's gonna detail stuff for people who have or haven't submitted the homework assignment. And I'm gonna try to come up with like a compromise. So yeah, that is the biggest update. So I'll definitely say, like, I don't know how often students actually check their email, because I have like sent out emails to students before, and then like sometimes I get a response, and other times like they say they didn't see it, and it's been like 3 days or something like that. So look out for check your email like at some point tonight, just so you're aware of what's going on. I might talk about it briefly tomorrow, but if you want like the full thing, just check it tonight. Okay, so now I'm going to give everyone 1 minute to set up their notebooks. Today we're talking about differentiability. So today we are not turning in an exit ticket. There is no exit ticket, but you are still turning in your class notes. So make sure you have the date, topic, your name, all that stuff. 10 more seconds. Okay. We're going to move on now to the first question of the do now, which I was hoping most people would get right, but there definitely was a lot of different answers. So the question is, the derivative of f of x at x equals c represents, and then the options are 1, 2, and 3. Can I get some volunteers in chat for the do now first question of what they got? So if you have an answer and like a reasoning behind your answer, feel free to submit it. Awesome. Gotcha. So I got a question about the homework packet from Jenny. Jenny, again, I will detail everything in the email after class at some point tonight. So just look out for that. Kalia, then Brianna, would you be able to come off mute? So first Kalia, and then share what your answer was for the do now.
I said E, but I wasn't sure.
Gotcha. So you chose all of them. Is there one that you weren't sure about, or like which ones do you feel more confident about?
I knew it had to be 2 in there, so yeah.
Oh, you said 2? You were sure like 2 was part of the answer?
Yeah.
Gotcha. And then, so why are you confident about that, about 2, about the slope of f of x being like the derivative?
Because isn't that basically finding like the tangent line or something?
Yep, that's exactly right. So 2 is definitely part of the answer. Brianna, you said you couldn't volunteer because there's too much noise in the back. Okay, that's totally fine. So I'll go through this really quick. So the answer is D, so it's 2 and 3. So remember the derivative, try to emphasize this before, but the derivative is always just the slope. Slope of the graph is the derivative, or like the slope of the tangent line, instant rate of change. These all mean really the same thing, right? So, and you don't necessarily have to write this out in your notebook just because it's the do now portion, but the derivative at a given point, let's say I have a graph here, and then I'm finding the derivative at this point. Well, basically I'm focusing on what the slope is at this point. And the slope at this point is very positive. So I know the derivative is going to be very positive, right? I know the slope is positive because this graph is going up, right? So the slope is going to be very positive. The slope of the tangent line, which is the same exact thing, it just makes it more, it just crystallizes what we're looking at more clearly, right? Because like the slope at this point is kind of hard to tell, right? But when I draw the tangent line, it's like, okay, the slope at this point is now very clear because the tangent line has the same exact slope. And then the instant rate of change is also the same exact thing as slope. So that's all, again, the derivative focuses on that. The slope, the instant rate of change, slope of the tangent line, they all focus on the same idea. Now, part 1, the function value of f of x when x equals c, this is not part of the answer because the function value, that's just asking us what this equals. So maybe at this point it's 2. That's cool, that's 2, but that doesn't tell us what the slope is. Like it could be any number like 10 or 100. The value of the function doesn't tell us what the slope is. So we're not focused on the function value, we're focused on the slope of the function at that point. So it's 2 and 3. Okay, so I saw for this question, I think a lot of people, the wording was a bit confusing for them at first because people were answering essentially which the following graphs is negative x cubed. And they were getting that right. One of these graphs is negative x cubed, I believe, but one of these graphs represents the slope of f of x. So can anyone, I saw a few correct answers. So can the people who are like kind of confident in their answers submit what they think the right answer was for the slope of f of x? So it's a slope graph, like as a derivative sketching type idea. Awesome, thanks, Kalia. So again, this goes back to our topic of derivative sketching, right? Where we have like, where we were given one graph, like we were given like one graph and then we have to like choose what the derivative sketch looks like. But the difference is this time we're not actually even given the graph. All we're given is a function. And then we have to be able to tell from the function what the derivative graph would look like. And I saw some right answers. So if I can get some more volunteers, that'd be great. I might cold call. Takira, would you be able to come off of mute and share what you thought about for this problem? Takira, are you there right now? Okay, how about is there Venia? Would you be able to come off of mute? Okay, guys, if you're like listening, I like really need you guys to like be paying attention to what's going on in class, and just have your face in the frame of your video and all that, and just be following along with your notes. Otherwise, I mean, we're just not going to make progress in learning about Calc AB. So I really like for everyone to have their notes out and be paying attention. Kalia, could you share what you said in the chat?
So I did I found a derivative for f of x and I got negative 3x squared. And then I knew that since it was negative, I had to concave down. And so I got C as the answer. Gotcha.
Yep, that's exactly right. So C is the right answer. For everyone who did the do now, it might be kind of confusing because at first you're like, okay, I don't have the original graph, right? We've done derivative sketching, but all those times I had the original graph and then I could kind of like look at the slopes and try to tell what the second graph was. But this time I'm not given the original graph, like I don't have it. However, here's where we like connect different concepts, right? Remember, all we're doing is the derivative. We're doing a derivative sketch. So we don't even need the other graph. We can just find the derivative of this, right? Which Kalia did power rule. So you negative x cubed is f of x, let's say. And if you do power rule, it'd be equal to, you bring the 3 down, right? So it'd be 3x, and then you subtract 1 from the exponent. So it'd be 3x squared, or sorry, it'd be negative 3x squared, because the original was negative x cubed. And then now we have this equation. We know this is what the graph of the slope graph, the derivative graph, is going to look like. So if it's negative 3x squared, we know what x squared looks like, right? It's going to be a parabola. And then if it's negative 3, that means it's going to be upside down. And that's all we really need to know. Like because it's x squared, we can eliminate answers like b right away and a right away, because that's clearly not a parabola. So then it's between d and c, and then we also know that it's negative, right? It's a negative x squared graph, so it can't be d. So our answer is c. And that's where it's important to really connect this idea of like, we're looking at derivatives and then like slope graphs and things like that, and they're all the same idea. So we can find the slope graph by finding the derivative, because the slope graph is a graph of the derivative. Okay, cool. So we're going to move on today to differentiability. So I would like people to copy this. So I'll just read that out loud. Differentiability, the definition is a function is differentiable at a given point if its derivative exists at that point, right? So it's a very simple definition. So we're going to kind of connect the idea of continuity and differentiability later over here. But for now, just understand that a function is differentiable if we can find its derivative. So like almost a lot of the things we've dealt with, like for example, negative x cubed, like we didn't do now, like f of x is equal to negative x cubed. We were able to find its derivative, right? We found its derivative, Clea did power rule, right? And we got negative 3x squared. So because we're able to find its derivative, we know that it's differentiable, because that's the definition. If we can find the derivative, then it's differentiable. Or if the derivative exists at that point, I guess, to be more precise. But make sure you have the definition copied. And then this is just a refresher. So when we're saying that we're trying to find a derivative, remember what that means. We're trying to find a slope at that point. So if we can find a slope, if there's a slope that exists, that means there's a derivative, right? And if there's a derivative, we can say it's differentiable. So that the slope of a function at that point, the slope of the tangent line, the instantaneous rate of change at a point. So again, these are all the same ideas because they're the same idea as a derivative. And if we can find these things, that means this function is differentiable. The next thing I would like everyone to write down is connecting non-differentiability and continuity. So a function must be continuous to be differentiable. You don't really have to write this down, but I would say a function must be continuous to be differentiable. Right, so remember for differentiability, right? Again, finding a derivative simply means we can find a slope. So like a function like this, it seems like, oh yeah, it's pretty easy. At this point, we can find a slope. It's like not hard, right? You can very clearly do it. At this point, you can find a slope. However, when a function isn't continuous, let's say a function looks like this, there's a jump discontinuity, right? And I'm asked, how do I find the slope at this point? Right? And it's not possible. Like how would I find the slope at this point? It just doesn't make sense, right? Because I have like a single point, and like the slope at this point, let's say, it just doesn't make sense. There isn't a slope. So if I'm asked to find the slope at this point, then sure, I can draw the slope. The slope is like the exact same because it's a line. But at some place like this, Or for example, I will draw a different graph. This is a good example. Like this is a good example of why a function needs to be continuous to be differentiable. But like this function is continuous, but it's still also not differentiable. For example, at this point, how do I find the slope, right? It's weird because there's like two lines going into it and it's not really clear what the slope is. Is it like this, or like, does the slope follow this line, you know, or does it follow that line? It's not very obvious. So there is no slope at that point. That means it's not differentiable, right? Because slope and derivative are the same thing. So we can't find the derivative, so it's not differentiable. Hopefully that makes sense. And so these are graphically, these are like the most obvious types of non-differentiable points. So at these type of points, it's not differentiable. So at points that are cusps, so I'll make it more like broad. So at any sharp corners are not differentiable. That means we can't find the derivative, right? And again, that makes sense. So any sharp corner, right? And I'm trying to find the slope, right? That's the derivative. At that point, like, how do I do that? I can't find the slope. It doesn't make sense. Like, I need something, a smooth corner like this, a smooth function, right? Then I can find the slope. But at a sharp corner, or as they say, a cusp, are not differentiable. Also, we already covered this, but a function must be continuous, right, to be differentiable, right? So we have a discontinuous function like this, right? So how would I find the slope here at an asymptote? Like that makes even less sense. Like what is the slope over here at x equals 0? Like I have absolutely no way to draw that. And because I can't draw a slope, again, to connect these ideas, because I can't find a slope, there's no slope of the tangent line, there's no instantaneous rate of change, all these ideas, that means there's no derivative. So if there's no derivative, then it's not differentiable. So if we can't find the derivative, then it's not differentiable. Next, I think this is probably the more confusing example, is a vertical tangent line. So this function is continuous, right? We just drew it like this. And you can almost be like, okay, I actually can draw a tangent line. So this is a vertical graph here. It goes like straight up, right? So if I draw a tangent line, it's like this, right? So it's like, okay, I can draw a tangent line. That's promising, right? It's not like these sharp corners where I like don't even know how to draw a tangent line, right? Or like at a discontinuity where I have absolutely no idea how to draw a tangent line, right? At least here I can draw a tangent line. But now we have to think about what is the slope of this? What is the slope of a completely vertical tangent line? Right? We know a horizontal tangent line, the slope is equal to 0, right? But for a completely vertical tangent line, we don't have a word for that. The slope is undefined. So in these cases too, it's still not differentiable when there's a vertical tangent line. So what I would like for people to have in their notebooks is like these 3 general graphs. Like you can draw it your own way. You don't have to write down every detail, but generally at cusps, at discontinuities, at vertical tangent lines, you're not going to have a differentiable function. And again, the reason is you can't really draw a tangent line with like a slope that makes sense. Again, even here, you can draw a tangent line, okay, but the slope doesn't make sense because the slope is undefined. Okay, cool. So I'm going to move on now to this you try. You don't have to draw this graph in your notebook unless you feel like it'll help you. But this is just visually, we're going to try to determine whether each of these points is continuous, differentiable, or neither. So I'm going to give everyone 3 minutes right now to try to solve these problems. 1 through 5, they should be relatively quick if you know what you're looking for. So your goal is to determine whether it's continuous, whether it's differentiable. And remember, if it's differentiable, that means it's automatically continuous, right? We said that a function must be continuous to be differentiable. And then, or neither. So start working on this. And then I'm going to answer Clarissa's question, which is it only linear equations that are differentiable? No, again, for example, a parabola, right? We can draw a tangent line, right? And the slope makes sense. Like this slope could be like, I don't know, 3 or something like that. I'm not sure exactly what the slope is, but that means it's differentiable. We can find the derivative. So I'll say you can write your answers out as like C, D, or N. And then once you finish the problems, I would like for people to just chat me like your sequence of answers, 1 through 5 in the chat box, please. And if it helps, remember our casual definition for continuity, right? So our definition was if you don't have to pick up your pen and you can draw it, then it's continuous. So it's pretty simple. Wu Chao, awesome. You're spot on. Good job. Give another minute and a half maybe. Can I get a few more answers in the chat? Thank you, Jordan. Awesome. Okay, Ruchal, do you want to take me through the first 3 of these and just take me through how you did each of the, or how you got to your answer?
For number 1, I looked at the graph and saw that there was, what do you call it, a cusp. So I was like, wait, yeah, there's a cusp right there. So I was like, that wouldn't be differentiable, but the thing is, it's still continuous because like you don't have to lift up your pencil, basically. For the second one, I said it was continuous, which means that x equals 0, but it wasn't differentiable because there's a vertical tangent line at x equals 0. And then for number 3, I said it was differentiable because at x equals 1, it's basically a parabola, and there's nothing wrong with it because it's still continuous.
Yep. Cool, awesome, thanks. Yeah, so just to go over that really quick, so for at -1, you don't have to pick up your pen, right? So we know it's continuous. Now the question is whether it's differentiable. And again, it's a sharp corner, and at any sharp corner or a cusp, you can't really draw a tangent line, right? It just doesn't make sense. How would I draw a tangent line here? So we know we can't find a derivative, right? It can't, because like there's no slope here. It wouldn't make sense to find a slope. Then at 0, we have a vertical tangent line with a slope that's undefined, so we also can't find the derivative. And at x = 1 here, it's continuous, right? But we can find the derivative, right? Because the slope, well, it looks like it'd be a slope of 0, just be a horizontal tangent line, which is acceptable for us. Jordan, can you take us through 4 and 5?
For number 4, I said it was neither because it's a cusp, and also you have to pick up your pencil. So that's neither. And then for 3, I said it was continuous because there's like nothing, it keeps going.
Gotcha. So yeah, for this first one, you made 2 great points. So first, it's not continuous, right? Well, actually, first you looked at it, so you saw that it's a sharp corner, so it's not differentiable. I would say you could do it even faster, perhaps, just by looking at if it's continuous or not, right? Because we see that we have to pick up your pencil for a point, right? Because there is a hole here, right? And our first rule, or one of our first rules was if it's not, like, for a function to be differentiable, it has to be continuous. And we see already here it's not continuous. So we don't even have to worry about if it's differentiable or not, because it's not continuous, so it can't be differentiable. So it's neither. And then for this last point, at 3, it is absolutely continuous. But another thing is it is also differentiable because we can draw a tangent line at 3, right? It would, since it's a line, it'd be, the tangent line would be like the exact same as this line. But it's not a sharp corner. It doesn't have a vertical tangent line. It is continuous, right? So it would also be differentiable. Okay, awesome. So that is like graphically how we can look at differentiability, right? We can determine just by looking at a graph whether this function is differentiable at a certain point or not. But what's more difficult, I would say, is determining stuff algebraically. So when we're not given a graph, and let's say it's like kind of hard to like graph it out. So obviously I could go to Desmos or my graphing calculator and put cube root of x in, and then I could just look at it and again just use the same strategies as before, tell if it's differentiable or not. However, what if I'm not able to do that? So one thing to do if it's differentiable, remember what is the ultimate definition of differentiability is if we can find the derivative. At a point. So the derivative must exist at a given point for it to be differentiable at that point. So I'm just going to find the derivative of cube root of x. So, well, I'll say f of x, I'm going to rewrite it, is x to the 1/3, right? Because so if it's a cube root, it's x to the 1/3. Square root is x to the 1/2, is x to the 1/2, right? Stuff like that. Hopefully that's an algebraic like pattern, you know. But if I find the derivative of this, it'd be 1/3 x, right? Because I'm bringing the 1/3 down, and then I am subtracting 1 from the exponent, so it'd be -2/3 because 1/3 minus 1 is -2/3. This is just power rule, right? And it's kind of confusing because there's fractions involved, but it's the same power rule. And then I'm going to simplify this to 1/3 x 2/3, right? I just brought the exponent down into the denominator, so now it's positive. And then, yeah, I'll just leave it like this. So it's like, cool, we found a derivative, right? We found a derivative. But we're told that each function below fails to be differentiable at a given x value. So justify this algebraically or geographically. So we're told that it's not differentiable at x = 0. So how can I prove that? I can just plug in 0 into this function here, right, into the derivative, and then I should get something that doesn't make sense. So if I plug in f of 0, right, it's going to be equal to 1 over 3 to the 0 to the 2/3, which is simply equal to 1 over 0, right? And obviously, this does not make sense, right? So that tells us, just because we found the derivative, right, which is the definition of differentiability, and then we plugged in a point, and we saw, wow, that does not make sense. So we know that at that point, there is no derivative, so it's not differentiable. Not differentiable at 0. Right, and then if I want to, I'll just show really quick what the cube root of x graph looks like. I think I'm like really bad at visualizing graphs, so I actually had to plug this in. But the cube root of x graph, it looks like this. And this looks like pretty okay at first, right? It looks like you can find a tangent line at any point, right? I could draw a tangent line here and find a slope. But what happens is at x equals 0, the graph gets completely vertical. And we learned earlier that when there's a vertical portion of the graph, it's not differentiable, right? Because if I draw the tangent line here, the slope is going to be undefined. Undefined. So that's what happens with cube root of x at x equals 0. So at x equals 0, we know it's not differentiable. We looked at it graphically, and we looked at it algebraically, and we showed that it's not differentiable. So I would like people to take maybe 3 minutes now to attempt the second problem, which is very similar to the first, but algebraically, for me, prove that whether it is differentiable or not differentiable at x equals 0. Sorry, I should have written that down, but x equals 0. And then once you get your answer, just please chat your name or your answer into the chat box. I'm going to just write a statement out just to make this clear. If it's differentiable, so yeah, that's just a definition of differentiability again. If it's differentiable at 0, that means we should be able to find its derivative at 0. And again, derivative, slope of the tangent line, instantaneous rate of change, all similar ideas. So I'll give 1 more minute. I would like some more submissions in chat. Okay, I'm gonna give like 30 more seconds and I'm going to cold call on someone or call on a volunteer in chat. Okay, Jordan, would you be able to come off of mute and just take us through how you got your answer?
I said it wasn't how you say
differentiable.
Differentiable,
yeah.
Because when I plugged in 0 for the derivative of x to the half power, I got 1/0. So
gotcha.
Yeah.
Awesome. Yeah, that's great. Can you take us through what you got for the derivative of x to the half power?
I got 1/2x to the half.
1/2x to the half. Okay. Yeah, I'll just take us through it really quick. So f prime of x, it's the same idea with power rule. So we bring the 1/2 down, subtract 1/2 from the exponent, so minus 1/2. So that'd be equal to 1/2x to the 1/2. Exactly what you got. And then if you want to simplify it to something that makes even more sense, it'd be 2 square root of x. Right. So if I plug in 0 for x, so f prime of 0, we're going to get 1/2 square root of 0 is obviously equal to 1/0. So that tells us right there, well, I wouldn't circle this because it doesn't exist. When we try to find the derivative at x equals 0, we're told that it doesn't exist, right? It just doesn't make sense. So that means, since we can't find the derivative, that means it's not differentiable. Awesome. Okay, so thank you, Jordan. And then I'm just going to draw x to the 1/2 to show what it looks like really quick. That is what the square root of x. This is the square root of x, right? So at x equals 0 at this point, well, you can kind of tell, like, how do I draw a tangent line? I don't even, like, it's a single point. I can't draw a tangent line. If it continued like this, maybe, then I can draw a tangent line, but it doesn't. So, okay, thanks everyone for coming to class. That is it for today. There is no exit ticket, but I'll just say look out for the email tonight again about the homework packet. Don't panic if you haven't done it. So yeah, just look out for that and make sure you read through it carefully. But thank you, everyone. See you, Kayla. See you, Clarissa. And then I can stay after class if anyone has questions.
There's one.
Yeah, what's up?